So today I want to talk about, so last time we talked about the Dane functions of solvable groups, and what I want to do today is I want to start talking about limits of spaces. In particular, I want to talk about asymptotic cones. So in order to talk about asymptotic cones, I first need an object called an ultrafilter. So I first need to define ultrafilters and ultralimits. So an ultrafilter is a finitely additive measure on the natural numbers that only takes on the values zero and 1. So trivially, if I define omega to be the function that takes S, a set of natural numbers, and is equal to 0 if, let's pick a number, if say 5 is not in S and 1 if 5 is in S, then this is a point measure. It's finitely additive. It's defined on every subset of the natural numbers, and it only takes on the values 0 or 1. This is an example of an ultrafilter, but this is not a very interesting example of an ultrafilter. It's not a very useful example of an ultrafilter. This is what's called a principal ultrafilter. A principal ultrafilter is an ultrafilter that is an ultrafilter that's supported on a finite at a single point. Principal ultrafilter is a ultrafilter of this form. If an ultrafilter is non-principal, then it has to be 0 on every finite set. Actually, and let me also add a condition, and let's call this measure omega. Let me also add the condition that omega of the natural numbers is equal to 1. So that we don't end up with a measure that's trivial. So a non-principal ultrafilter is going to be 0 on every finite set, because if you have a finite set where the measure is equal to 1, then that means that because this measure is finitely additive, then the sum of the measures of every element of that set is a finite sum, is equal to the measure of the set. Because the measure only takes on the value 0 or 1, that means that one of those elements of the set had to take on the value 1, and the rest of them had to take on the value 0. And so now you've got, well, a principal ultrafilter. So if you have a non-principal ultrafilter, then it takes on the value 0 in every finite set. And the way we think of non-principal ultrafilters is that we think of sets where the measure takes on the value 1 as large infinite subsets of the natural numbers, and sets where it takes on the value 0 as small infinite subsets, as small subsets of the natural numbers. And you can't take a finite union of small sets and get a large set, or if you take a large set and you change it by a small set, it stays a large set. So the utility of the ultrafilter is that it lets us define ultralimits. So if I have a sequence of numbers, a sub I, is a bounded sequence then without loss of generality, let's suppose it's bounded between 0 and 1. Then we can use because this is a bounded sequence, it has a limit point, it has a convergent subsequence. What ultrafilters let us do is, because this is a bounded sequence, this has a convergent subsequence. In general, it may have many different convergent subsequences. What an ultrafilter lets us do is it lets us pick one of those convergent subsequences. Then we define limit, the ultralimit of a sub I as follows. So consider, so how do I want to do this? Yeah, so we define the ultralimit of the a sub I to be, let's say, L, where for every epsilon greater than 0, the set of I such that a sub I is contained in the interval L minus epsilon to L plus epsilon is a large set. That is, omega of this set is equal to 1. And this, so what can we say about this? If omega is a non-principal ultrafilter, then this is a limit point of the sequence. But the important thing is that because omega is finitely additive, there always has to be some number like this. For any epsilon greater than 0, we can cover the interval from 0 to 1 with finitely many intervals of length epsilon. Those finitely many intervals of length epsilon partition the sequence into 1 over epsilon many subsets, 1 over epsilon many disjoint subsets. Because the entire set of natural numbers has measure 1, one of those finitely many partitions has to have measure 1, and exactly one of those partitions has to have measure 1. So that means that, and what that lets us do is it lets us narrow down where the ultralimit is. So if we have some sequence of natural numbers between 0 and 1, say here's our interval from 0 to 1, and here's our sequence of points, what we can do is we can find the ultralimit of this sequence by doing a divide and conquer argument, or by repeatedly dividing the interval. We can say, okay, is the ultralimit less than 1/2 or bigger than 1/2? So we divide the interval into the interval from 0 to 1/2 and the interval from 1/2 to 1. One of these sets is large, say this one is large, and the other one has to be small. And whichever one is large, the ultralimit has to lie in that subinterval. And so we divide that in half. And again, well, if we divide a large set into finitely many pieces, then one of those pieces has to be large, and the rest of them have to be small. So one of these is going to be large, and the other one is small. And then we repeat again and again. We divide this into 2 pieces. One of these is large, one of these is small. If we divide this into 2 pieces, one of those is large. And this eventually converges, and this gives us a limit. And so this ultralimit always exists. For any bounded sequence. It's unique. It's unique because if I had 2 different points with this property, say L and L prime, then I could take an epsilon neighborhood of L prime and an epsilon neighborhood of L, so that, well, by the definition of the ultralimit, the set of numbers such that a sub I lies in this interval has to be large. The set of numbers such that ai lies in this interval has to be large. But then I'd have two disjoint large sets, and that would mean that the measure of the entire set of natural numbers would have to be it would have to be 2, and that would violate the definition of an ultrafilter. So this limit exists. This limit is unique. Furthermore, it satisfies all the usual notions of limit. This is a limit point. I should say, I really should define this. Let me say, so if omega is a non-principal ultrafilter, and a sub I is a bounded sequence, because if omega is a principal ultrafilter, then this construction is trivial. If omega is a principal ultrafilter, then the omega limit of a sequence is just one particular term of that sequence determined by what point that principal ultrafilter is supported on. So if omega is a non-principal ultrafilter, then every large set has to have infinitely many points. So that means that the ultra limit of a sub I is a limit point of a sub I. And we can actually say something a little stronger than this. We can actually say that if a1 sub I up to, so if I have finitely many different sequences, so a1, a2, up to ak, if I have finitely many different bounded sequences, then not only is the the ultra limit of each sequence a limit point of that sequence, but we can do all of that simultaneously. We can say that the ultra limits of the ultra limits of all the sequences are a limit point of the sequence ai1 up to aik. So not only does this let us choose a convergent subsequence for every sequence, but it allows us to choose that convergent subsequence in a consistent way. Not only can we choose a convergent subsequence of the A1s and a convergent subsequence of the A2s and so on, we can actually find a subsequence so that all of the A sub i's, or all of the AIJs converge simultaneously. So this is one more property, and you can also prove that this is linear. So what this does is it extends the notion of a limit from convergent sequences to bounded sequences. This provides a limit for every bounded sequence. And the exact limit of a bounded sequence is going to depend on the ultrafilter. I mean, they're clearly non-convergent sequences. So for instance, the sequence 0, 1, 0, 1, 0, 1, 0, 1, by the properties we have here, the ultralimit of that sequence has to be either 0 or 1. It has to be one of those limit points. And exactly which limit point it is going to depend on the choice of non-principal ultrafilter. It's going to depend on whether the set of odd integers is a large set or whether the set of even integers is a large set. And by the definition of an ultrafilter, one of those, and exactly one of those, has to be a large set. Is this okay so far? So there's one thing missing from this construction. I've claimed that if I have a non-principal ultrafilter, then I can construct an ultralimit in this fashion. But it's not at all clear that a non-principal ultrafilter exists. So in fact, there is a non-principal ultrafilter. In fact, there are a lot of non-principal ultrafilters. But the proof requires the axiom of choice. The proof is the standard Zorn's lemma argument. So there exist, if you accept the axiom of choice, then there exist functions like this, there exist ultralimits like this. But this is a lot of the things we're doing are going to be, we're doing today are going to be slightly non-constructive in the sense that the construction involves the axiom of choice. Okay? Is this okay so far? Okay, so what can we do with this? So by the same argument, I guess I erased that. By the same using these same arguments, we can also define if X is a proper metric space, which is to say that all balls are compact, then we can define the ultralimit of bounded sequences in X. A sub I is a bounded subsequent, is a bounded sequence then we can define the ultralimit of the A sub I exactly the same as for the real numbers. So where we define this limit to be equal to L if and only if for all epsilon greater than 0, the set of points, the set of indices such that A sub I is in the ball of radius epsilon around L is large. And if this is a proper, and if X is a proper metric space, then this limit has to exist essentially by the same argument as for the real numbers. If X is a proper metric space, then, and A sub I is a bounded sequence, then A sub I stays in, say, the ball of radius R, and then we can cover the ball of radius R by finitely many balls of radius epsilon. Because we can cover this ball by finitely many balls of radius epsilon, that divides the set of indices into finitely many subsets depending on which of these small balls they end up in. And so we can use that to say, okay, well, if a set of points that land in this ball is a large set, then the ultralimit has to lie inside that ball. And then we can do the same argument as before. We cover that we cover that ball by even smaller balls, pick one of those, cover that by smaller balls, pick one of those, and so on and so forth until we get a ultralimit. So we can use these ultrafilters to extend limits to all bounded sequences. We can use ultrafilters to extend limits to all bounded sequences of points in a proper metric space. But what we can also do is we can use ultrafilters to extend the notion of Gromov-Hausdorff convergence to arbitrary sequences of metric spaces. So we can define ultralimits of spaces. So if X sub I with metrics D sub I is a sequence of metric spaces, And if, let's say, we pick base points in each of these, x sub I, little x sub I, in x sub I is a sequence of base points. We define the ultralimit of this sequence as the set of bounded sequences of points. But now, because we're looking at a sequence of different metric spaces, in order to say that a sequence of points is bounded, what we mean is that the distances to xi, the distances to these base points are bounded. So we're looking at the set of sequences a sub I such that the distance from a sub I to x sub I is bounded. How do I want to say this? So let me say that there exists some c greater than 0 such that the distance from x sub I to a sub I is less than c for all I. So we define the ultralimit as the set of bounded sequences modulo an equivalence relation, where that equivalence relation is that we say that the sequence a sub I is equivalent to the sequence b sub I if the limit of the distance from a sub I to b sub I is is equal to 0. So the reason we choose bounded sequences of points is so that we can define this equivalence relation. Since a sub I is bounded and b sub I is bounded, that means that the distance from a sub I to b sub I is bounded, and so this ultralimit exists. And I claim that, oh, sorry, I should put a metric space on. I should put a metric on this. So this is my set of points. I'm going to make it a metric space by defining a metric. So let's let d sub omega of the sequence a sub I to the sequence b sub I be equal to the omega limit, the ultralimit of the distance from a sub I to b sub I, where I'm going to use square brackets to denote the equivalence class of the sequence a sub I. And then I claim that, in fact, this is a complete metric space. And so checking that this is a metric space is not too hard to do. To check that it's a metric space, we mainly need to check the triangle inequality. So we want to look at the distance between a point a sub I and a point c sub I. But by definition, this is equal to the limit, the ultralimit of the distances between a sub I and c sub I by applying the triangle inequality. So this is the distance between a sub I and c sub I evaluated in the metric space x sub I. So I guess maybe I should put subscripts on these distances. Maybe I should put that this is d sub I, and that this is d sub I, and this is d sub I. By the triangle inequality to apply to each individual metric space, this is less than or equal to the ultralimit of di, the distance from ai to bi, plus the distance from bi to ci. And then by the linearity of the ultralimit, this is equal to the omega distance, the ultra distance between a sub I and b sub I, plus the limit distance between b sub I and c sub I. And so we get the triangle inequality. And in particular, this also tells us that this also tells us that the distance is well defined. If a sub I and b sub I are equivalent under this equivalence relation, then that means that this term ends up being 0, and we actually get equality in this inequality. Is this okay so far? Are there any questions so far? Okay. Sorry?
If you get the constant sequence, it gets you a construction of the completion.
Sorry?
If you get the constant sequence of space, it gets you a construction of the completion.
Not quite. So I said that this. I said that this extends the Gromov-Hausdorff limit. But let me specify. So if x sub I, if the x sub I, I guess to avoid base points for now, let me say that if the x sub I are compact proper metric spaces, and if x sub I converge to x in the Gromov-Hausdorff sense, and if x is proper, then the ultralimit of the x sub I is equal to x. But in general, in general, you can run into problems. So for instance, if you take the metric on the set of integers, where the distance between any two integers is 1. So this is the discrete metric on the set of integers. Then this is a metric space, and if you take the ultralimit of a sequence of just that metric space, then you don't end up with it. You don't end up with the same. The limit ends up being different from the sequence. The limit ends up being an uncountable set of points, whereas the sequence is a sequence of countable sets of points. Basically, because the way that you prove this, lemma is basically to say, okay, if I have a sequence of points in the x sub I, how do I get a, so how do you prove this? Well, you want to construct a map. You want to construct maps from the ultralimit to x, and you want to construct a map from x to the ultralimit. And one direction is not too hard. If the x sub I converge in the Gromov-Hausdorff limit to x, then for any point in x, I can view that point as a limit of a sequence of points, 1 in each x sub I, and that can be my bounded sequence of points in the ultralimit of the x sub I's. The other direction is a little bit harder, but to prove the other direction, well, if x sub I converge to x in the Gromov-Hausdorff metric, then I have a map from each of the x sub I's to x that gets where that map gets closer and closer to an isometry. And so if I have a sequence of points, 1 in each x sub I use those maps to get a sequence of points in x. And because because x is a proper metric space, that sequence of points in x has an ultralimit, and so that's going to be my map from the ultralimit of the x sub I's to x. I'm going to take a sequence of points in the x sub I's, use the Gromov-Hausdorff distance to get a sequence of points in x, and then use the ultralimit on that sequence of points in x to get a point in x. Is this okay? So this really does use the properness of x in that final step. This uses the properness of x to construct this map. And so when your space doesn't start out, when your space or when your limit is not proper, then it's going to be, then you get something that's typically much larger than the Gromov-Hausdorff limit. Okay? So yeah, so in many cases, so I said this was a metric space. I proved the triangle inequality. I asserted that this is a complete metric space, and you can prove that it's complete using a version of using a diagonal argument. What else can we say about this? So what else can we say about this? One of the big things, one thing we can say about this is that if the sequence of spaces are geodesic, then the limit is geodesic. And the reason why we can do this is because, well, if I have, say, x and y in this ultra limit, and if I have, say, x is the equivalence class of a sequence x sub I, and y is in the equivalence class of a sequence y sub I, then we can let gamma sub I be the geodesic, or at least a geodesic, from x sub I to y sub I. And then we can define gamma of t to be the limit of the gamma sub I. So we can say, define this as the limit of, we can define gamma of t to be the limit of the sequence gamma sub I of t, and then this is a geodesic from x to y. And this is actually, so this fact that if x sub i's are geodesic, then the limit is geodesic. This is actually a sort of special case of a particular construction, or of a particular fact, which is that this ultra limit is functorial. More generally, if f sub I is a sequence of maps from x sub I to y sub I, and let's say let's give these spaces base points. Let's say that this has base point x sub I, and that the y's have base point y sub I. If this is a sequence of maps, and let's say that these are all Lipschitz and that they all have uniform Lipschitz constants. So these are L Lipschitz maps. Such that the distance from f of x sub I to y sub I is bounded. Then let's call it f omega of x. So the f omega, then I can define a function f omega from the ultra limit of the x sub i's to the ultra limit of the y sub i's by letting f omega of the sequence x sub I be equal to the equivalence class of the sequence of f sub I of x sub I, And then this is a Lipschitz function, is an L Lipschitz function. So in this construction, we applied this to geodesics. We said our maps f sub I were a sequence of geodesics, were a sequence of maps from the interval 0, 1 to our space. By this, the interval 0, 1 is proper, so the ultralimit of a sequence of intervals is an interval. And so those geodesic segments converge to a geodesic segment from x to y. But more generally, if I have a sequence of maps from x sub I to y sub I that satisfy some mild property, saying they have to be bounded so they can't get infinitely far away from the base point, they have to be uniformly Lipschitz so that points don't get separated too much, then they're going to converge in the ultralimit. Then they're going to descend to a map from the ultralimit of the x sub I to the ultralimit of the y sub I. And so a lot of things, so we can construct a lot of objects in the ultralimit basically by constructing corresponding objects in the sequence of spaces and then taking a limit. The difficult thing about working with ultralimits is that we can very rarely, or it's generally difficult to go the other way. There are generally going to be a lot of structures in the ultralimit that don't correspond necessarily to structures in the original spaces. The standard example is if I take my base is x sub I to be, say, 1 over I times the integers. With the usual Euclidean metric, then the ultralimit of these x sub i's is the same as the Gromov-Hausdorff limit of these x sub i's is R. And R is a geodesic metric space, but R is a geodesic metric space, but the x sub i's are not. R has geodesics between any pair of points, but the x sub i's are just disconnected sets of points. The best we can say, just knowing that, the best we can say about the spaces x sub I, just knowing that the ultralimit is equal to R, or that the ultralimit is geodesic, is something like an approximate midpoint property. If you know that the ultralimit of a sequence of spaces is geodesic, then that means that for any 2 points in the limit, there's a geodesic segment between them. That geodesic segment has a midpoint, and then that midpoint is the limit of a sequence of points in all the spaces. And so on some subsequence of those spaces, that midpoint is going. Let me write this down. So this is an example where our spaces are not geodesic, but the limit is geodesic. More generally, if the ultralimit of the x sub i's is geodesic, then the best we can say is that that infinitely many of the x sub i's satisfy an approximate midpoint property. If x sub I is a sequence if x sub I and y sub I are sequences of points in x sub I, then we can find approximate midpoints between x sub I and y sub I infinitely many times by using the geodesic property of the asymptotic cone, or sorry, of the ultralimit. then so if I have two sequences of points x sub I and y sub I, then the corresponding points in the asymptotic cone have a midpoint in the asymptotic cone. Let's call it m sub I, or let's say it's represented by the sequence m sub I. And then the limit as the limit, the ultra limit of the distance from x sub I to m sub I in the ith metric space is going to be equal to the limit of the distance from y sub I to m sub I in the ith metric space is equal to half of the distance between x sub I and y sub I. So the best you can generally say, if the ultra limit of the x sub i's are geodesic, then you can find approximate midpoints between pairs of points sort of for infinitely many spaces. The limit as there's some convergence, there's some subsequence of the natural numbers such that the limit of the distance from x sub I to m sub I is the distance from y sub I to m sub I is half the distance from x sub I to y sub I. So we have approximate midpoints, not an exact midpoint, not exact midpoints because of, for instance, this example here where the x sub i's are the sets of rational numbers with denominator I. But approximate midpoints. We have, for all these pairs xi and yi, we have some point that's almost the midpoint. Is this okay?
How would you show that R is the ultra limit?
Sorry?
How would you show R is the ultra limit?
Of those x sub I? Well, so in that case, those x sub I converge in the Gromov-Hausdorff limit. Do you know the Gromov-Hausdorff limit? Yeah, so those converge in the Gromov-Hausdorff limit. So they also, so the ultra limit is the same as the Gromov-Hausdorff limit.
Can you see directly, like if I take
Sure.
the base point?
Okay, sure. So if you haven't seen these before, it may be good to try to construct some of the maps back and forth. So in this case, if we want to look at the So if we want to go from the limit of these points, so 1 over I times the integers, in order to show that this is the same as the real numbers, we want to construct maps back and forth. So we want to construct a map to R. We want to construct a map from R to this ultra limit. And so what can we do? Well, one direction is not too hard. One direction can be so actually, well, neither direction is terribly hard. So let's just do them. So if I want to construct a map from the ultra limit of this to R, then I have to take the set take a bounded sequence of rational numbers with denominator I and construct a real number. And so, if A sub I is in this ultra limit, then the A sub I are a bounded sequence of rational numbers. In particular, they are a bounded sequence of real numbers. And so we can define, let's say, f of these A sub i's to be the ultra limit of the A sub i's. And you can check that if I have two sequences A sub I and B sub I that are equivalent in this ultra limit sense, then they map to the same real number, then they have the same ultra limit. On the other hand, if I have a real number, we can define, let's call this map G. We can define G of x I want to construct some sequence, I want to construct some bounded sequence of rational numbers with denominator I. And so what I do is I just pick the closest, for each I pick the closest rational number. So I define this to be the ultralimit of the sequence of points of the form x sub I over I. Or x, so this is the largest integer less than or equal to x times I, divided by I gives us a rational number in this set. And this sequence converges in the usual convergent sequence sense to x, and so it also converges in the ultralimit sense to x. So there are things to check here, and you can check that these maps are isometries, that these maps are inverses of one another, that sort of thing. But this is what the maps are going to look like. Is that okay? More questions? Okay. So yeah, so we have functoriality, we have Gromov-Hausdorff condition to convergence. So yeah, so like I said, this is a way of extending Gromov-Hausdorff convergence so that it applies to every sequence of spaces, which is a really nice. I mean, it's a nice thing to have. The price you pay for getting that, the price you pay for extending this limit to arbitrary sequence of spaces, well, is a couple of things. Is one, that these limits can become much more complicated than your original sequence of spaces. I mean, we saw this already. That if you take the discrete metric on the integers, so if you take the integers with the metric that the distance between two distinct integers is 1, that's a countable set of points all separated by distance 1, then the ultralimit of just repeating that metric space infinitely many times is different from the original metric space. It's an uncountable set rather than a countable set. So you pay. So one of the prices you pay is that your limits can be much more complicated than your original spaces. The other price you pay is that well, so everywhere we've written this, we've written the limit sub omega of these spaces. So the limit with respect to this ultrafilter. And in general, we can't avoid that. If we have the ultralimit that we get from this construction is going to depend very strongly on the ultrafilter. And you can construct sequences of points that have uncountably many possible different ultralimits, or sequences of spaces that have uncountably many different possible ultralimits, depending on your choice of ultrafilter. But that's just there's no way around it. That's just what happens. So is this okay so far? Okay. So the asymptotic cone of a space, and again, I shouldn't really say the asymptotic cone because, like I just said, the ultralimit of a sequence of spaces can depend very strongly on the choice of ultrafilter. So an asymptotic cone, the idea behind the asymptotic cone of a space the idea behind the motivation for the asymptotic cone is that you want to look at a space from infinity. You want to take a space that might be discrete, and then you want to zoom in or zoom out further and further. If I start with the grid of side length 1, then I zoom out by a factor of 2, I get a grid of side length 1/2. I zoom out by another factor of 2, I get a grid of side length 1/4. And so on and so forth. As I zoom out further and further, I get grids with finer and finer spacing, and they converge in the Gromov-Hausdorff sense to the plane. The reason that we want to define ultrafilters here, the reason that we want to use ultrafilters and ultralimits here, is that in general, if I take a space and I zoom out further and further, it's not going to converge in the Gromov-Hausdorff sense. I mean, you have all sorts of curvature blowups and dimension shifts and so on and so forth. And so to fix that, we use ultralimits. So if X is a metric space, and let's say let's give it metric D is a metric space. If P sub I in X is a sequence of base points, if R sub I is a sequence of scaling factors, and if omega is a non-principal ultrafilter, I'm going to let the cone with respect to omega of the metric space X with base points P sub I, scaling factors R sub I, I'm going to define this as the ultralimit of the sequence of spaces X, always the same space, but we're going to put different metrics on that space. The metric is so we're going to put the original function D divided by R sub I for the ith metric on this space, and I'm going to always use this, I'm going to use this sequence of base points P sub I. I want one more condition here. I want R to go to infinity as I goes to infinity. So I have a sequence of scales that goes to infinity. I define the cone of X with respect to this sequence of base point, this sequence of scales, this ultrafilter, to be the ultralimit of X with respect to the metric D over R sub I and the base point P sub I. So these metric spaces are a sequence of rescalings of X, and then we're taking the ultralimit to find the limit of this sequence of rescalings. Is this okay so far? So
Do you allow P to go to infinity?
the base points? Yeah, so we put no condition on the base points. They can be bounded, they can be constant, they can go to infinity. We put no condition. In general, what I'm going to say in a moment, in general, this is the definition we make for arbitrary spaces, for non-homogeneous spaces. But for the applications that we're going to be using this for, we're going to mostly be using this for geometric group theory. And in geometric group theory, all of our spaces have co-compact group actions. So if X has a co-compact group action, then the choice of base points doesn't matter. If X has a co-compact group action, then the choice of P sub I doesn't matter, because the only thing that we use the base points for when we construct the ultralimit is we use them to decide what sequences are bounded and what sequences aren't bounded. If X has a co-compact group action, then we can find, here's our space X, here's some compact fundamental domain, and we can just translate we can just translate all the P sub I so they lie in that compact fundamental domain, and then the ultralimit we get, the set of bounded sequences we get, is exactly the same as if we chose the base points to be constant. So if X has a co-compact group action, then we can just drop the sequence of base points. We don't care about the sequence of base points. Furthermore, we have dependence on the ultrafilter, and we also have dependence on this sequence R sub I. But we don't need both of these. In fact, if I change R sub I, if R sub I are a sequence of scales and R sub I go to infinity, and if omega is an ultrafilter, then I can write the asymptotic cone with respect to omega of X pi Ri did I get the, oh, I got the, yeah, XPIRI. This is the same as the asymptotic cone with respect to some different ultrafilter of X PI I for some and the reason for this is that the ultrafilter has a lot of control over, changing the ultrafilter gives you a lot of control over, over this limit. So before we define an ultrafilter, so for instance, if I take an, if I decide that I want to construct a version of the ultralimit that ignores all the points that have odd index, that ignores A1, A3, A5, A7, and so on, then I could just declare, okay, I'm going to construct an ultrafilter where the set of even numbers is large, and that means that the set of odd numbers is small, and so I could ignore the entire set of odd numbers. If I want to construct an ultrafilter that only pays attention to the points in my sequence that have index a power of 2, A1, A2, A4, A8, A16, and so on, I can just declare that all the numbers that aren't a power of 2 are small, and then I have an ultralimit that ignores everything that doesn't have an index that's equal to a power of 2. And the same thing applies here. If I have a sequence of scales that go to infinity, then either I can take an ultrafilter, or I can take an asymptotic cone like this, or I can take an asymptotic cone where all my scaling factors are just I, and then just use the ultrafilter to ignore all the values of I that aren't close to one of the R sub i's. So in fact, if X has a co-compact group action, we don't really care about the choice of base points. If X has a co-compact group action, we don't really care about the sequence of scales. And so frequently we'll write this just as X sub omega. We'll just drop the, we'll drop the sequence of base points, we'll drop the sequence of scales, and we'll just refer to it as some ultralimit depending on some ultrafilter. Is this okay so far? Okay. And for and moreover, if our sequence of spaces actually converges in the Gromov-Hausdorff sense, then none of these choices matter at all. If our sequence of spaces actually converges in the Gromov-Hausdorff sense, then it has a unique ultralimit. Okay. So what else do I want to say? So is this okay so far? Okay. Let me say one more thing, and then we'll look at an example. So one last thing. If X has a co-compact group action, then the asymptotic cone of X is homogeneous. So one of the big applications of this construction is that it lets us take spaces from geometric group theory, spaces with co-compact group actions, and turn them into spaces that are actually genuinely homogeneous. And the proof of this uses the same construction we saw before. If I have a sequence of maps between spaces in a sequence, then I can take a limit of that sequence of maps. So if I have X sub I and Y sub I are elements of X omega, then because there's a co-compact group action, there's a sequence f sub I of isometries such that f sub I of x sub I is close to, is a bounded distance away from x sub I, from y sub I. So because I have a co-compact group action, I can take any point close to any other point by applying the group action. And so these f sub i's are isometries. So they're also isometries with respect to the rescaled metric. And with respect to the rescaled metric, this distance goes to 0. The distance between f of x sub I and y sub I over I goes to 0. So if I take their limit, if I define a map f omega that takes the sequence z sub I, or the limit of the sequence z sub I, to the limit of f sub I of z sub I, this is an isometry because all the f sub i's are isometries, and this takes x sub I to y sub I. So if I start with the co-compact group action, then I end up with a homogeneous space. Is it okay? Okay. So let's take a look at an example to see what sort of stuff can happen. So the easy example is what we've seen already. The easy example is if I take x to be the set of integers, if I take x to be the unit lattice in Rn, then the asymptotic cone is going to be the plane Rn. And this is exactly the same thing that we did before when we said that the limit of 1 over I times the integers is the real numbers, except we've just added a couple of dimensions. But you can see what happens here. We take something discrete, we take this unit lattice, and we rescale it over and over to get finer and finer lattices. And those lattices converge in the Gromov-Hausdorff sense to Rn, and so they converge in the ultralimit sense to Rn. And you can see how, well, we start with a co-compact group action on these lattices, and that co-compact group action turns into a homogeneous, that co-compact group action on the lattices makes the limit into a homogeneous metric space. It makes it into a plane. So this is the easy example. But because it's the easy example, you don't see some of the strange things that can happen in asymptotic cones here. So let's take a look. So the slightly harder example is if I take a slightly more complicated space. So instead of taking x to be z, and let's take x to be the infinite 3-regular tree. So the infinite 3-regular tree, we have some point, and then we just draw 3 edges coming out of each point, and 3 edges coming out of each of those points, and so on and so forth, all the way out to infinity, right? So what does the ultralimit what does the asymptotic cone of this infinite three regular tree look like? Well, now, if I take rescalings of this tree, where the length of each edge is 1/2, 1/3, 1/4, 1/5, and so on, those don't converge in the Gromov-Hausdorff sense. So here we actually do have to use the ultralimit picture. And the ultralimit picture is a little bit hard to use. So the way I'm going to construct x omega is I'm going to try to construct it piece by piece. I'm going to find objects in this sequence of spaces and then claim that they also show up in the ultralimit. And we saw this before, that if you have a sequence of geodesic metric spaces, then the limit is geodesic. We're going to do the same thing here. We're going to try to find features of this tree and conclude that the same features exist in the ultralimit. So for example, let's call this point P. We know that that the ultralimit has to have some point consisting of a sequence of just P repeated infinitely many times. So we have a base point P in the tree, and we have a base point P in the ultralimit. And this base point has infinitely many geodesics running through it. So here, is there some colored chalk? I think there's some colored chalk, little bits of colored chalk. So this tree has geodesics running through it. And a sequence of geodesics in the space. And since for the asymptotic cone, our sequence of spaces is just rescalings of x, we can take it to get a sequence of geodesics in our space. We can just take this one geodesic and rescale it infinitely many times. A sequence of geodesics in x is going to converge to a geodesic in the asymptotic cone. So I have at least one geodesic running through P, but I have infinitely many geodesics running through P over here. So if I have another geodesic like so, what happens to that? Well, this geodesic, again, has to converge to a geodesic over here. Furthermore, how is it related to this previous geodesic? Well, in my original space, these geodesics, they meet at P, they overlap for some finite distance, and then they never meet again, right? Because this is a tree, and once they separate, they never meet again. So what's going to happen over here? Well, let's take some, so if I take a point here, this point here is going to be a sequence of points in rescaled. This point here is going to correspond to a sequence of points in x. And it's going to be a sequence of points in x that lie along this geodesic, and such that the distance from P to that sequence of points, in here, let's say this distance is 1. In order for a sequence q sub I of points along this geodesic to converge in the asymptotic cone to a point that's distance 1 from the base point, that means that the distance between P and q sub I has to be on the order of I. So if I want to construct a sequence of points that converges to this, that's going to be a sequence of points that's distance 1 from the base point. Here's q1, q2, q3, so on and so forth. Right? Same thing if I want to, same thing if I have, here's my other geodesic here in green. Same thing if I want a point of distance 1 away from the base point along this geodesic. That's going to correspond to a sequence of points, say, s sub I. And if this distance is also 1, that's going to correspond to a sequence of points s sub I that are distance s1, s2, s3, s4, all distance 1 away from my base point. And so if I want to know the distance between this point and this point, it's going to be the ultralimit of the distance between q1 and s1 divided by 1, q2 and s2 divided by 2, q3 and s3 divided by 3, q4 and s4 divided by 4, and so on. But because this is a tree, I know the distance between q sub I and s sub I. The distance between q sub I and s sub I is the distance from here to here. You have to backtrack along the red geodesic until they meet, and then go forward along the green geodesic until you hit S sub I. And so that means that the distance from Q sub I to S sub I is going to be 2I minus, in this case, I guess it's 2I minus 4 because they separate at distance 2. And so the distance in the asymptotic cone between the point corresponding to Q sub I and the point corresponding to S sub I is going to be the ultra limit of 2I minus 4 over I is equal to 2. So what that means is that if I start at my base point and I go out distance 1 along the red geodesic and I go out distance 1 along the green geodesic, then the distance from here to here is 2. And the same thing is going to happen no matter how far I go out. The distance between any point on the red geodesic and any point on the green geodesic, or the geodesic between any point on the red geodesic and any point on the green geodesic, is going to be a path that goes back to the base point and then goes out to the other point. So that means that really this picture is accurate. That if I have two geodesics like this, then the images in the ultralimit are going to be two geodesics like this that only intersect at the base point. And so is this okay so far? And so I can do this. I can do the same thing. I have uncountably many geodesics that pass through P. This is an infinite tree, so I have uncountably many geodesics that pass through P. And I can apply this same argument to any pair of those geodesics. If I take any two of those geodesics and they're going to intersect at P, they're going to overlap maybe on some neighborhood of P, but that neighborhood is going to be finite. And so when we do this repeated rescaling, that neighborhood is going to converge to a point. That neighborhood is going to collapse to a point. And so if I take any two distinct geodesics through P, their limits are going to be distinct, and their limits are going to only intersect at P. So just to start with, I know that the ultralimit of the infinite three regular tree has to contain uncountably many geodesic rays through infinitely many geodesic rays through P, and that the metric on those infinitely many geodesic rays is I think I've heard this called the Paris metric. Basically, that to go from any point to any other point, you have to go through Paris on your way. It's supposedly based on the French train system, but so we have uncountably many rays through P with this metric, but by what we've seen before, we know that there has to be a lot more than this as well. Because remember, if X has a co-compact group action, and the infinite regular tree certainly has a co-compact group action, then the asymptotic cone has to be homogeneous. So if you have one point that has infinitely many, uncountably many geodesic rays coming out of it, then that has to hold true for every point. Then in fact, every point has to have uncountably many geodesic rays coming out of it. And where do these come from? Well, so let's say I take, let's try to figure out where, say, these come from. Actually, I already have this point labeled. So let's say, in particular, this point here, the limit of the Q sub i's has to have uncountably many geodesic rays coming out of it. And where do these infinitely many geodesic rays come from? Well, I want to look for paths that go out to Q sub I and then diverge. So let's draw a geodesic ray out of Q1, out of Q2, out of Q3, out of Q4, and so on. This is a sequence of geodesic rays. So it has to converge in the ultralimit in the asymptotic cone to a geodesic ray. And because this is a sequence of geodesic rays based at Q1, and based at Q1, Q2, Q3, Q4, and so on, the limit in the asymptotic cone has to be a geodesic ray coming out of Q1, or coming out of this point here, out of the equivalence class of the Q sub i's. And the same thing if I chose a different set of rays coming out of these Q sub i's, I would get a different ray. And if I chose something intermediate, say alternate between these guys, or say I go partly along these guys and then turn off, then I'm going to get a different geodesic ray. And so there are infinitely many choices I can make here. There are uncountably many geodesic rays that come out of Q sub I. And the same thing is going to happen if I pick some point along here. I can do the same thing. I can find uncountably many geodesic rays coming out of that, and then uncountably many geodesic rays coming out of that, and so on and so forth. So I end up with an asymptotic cone where every point has uncountably large degree, where every point has uncountably many geodesic rays that all separate at that point. Is this okay so far? In fact, this is an example of something called this is an example of something called a real tree. Yeah?
An example of a group which has compactly on that infinity 3 regular tree.
The group of all isometry, the isometry group of the tree. Sorry.
Do you say, can one see the number 3 in the limit?
No, you can't. So you can't see. So exactly the same construction would work if I had a 4 regular tree or 5 regular tree.
That's the same limit.
Yeah, the same limit. So this is. So this is an example of is what's called a real tree. So a real tree, Gilles talked about these yesterday, but a real tree is a metric space. There are a couple ways we can define this. So we can define this as a metric space such that every triangle has a in which triangles are tripods. Which is to say that that for all x, y, and z in x omega, the geodesic segments, if gamma xy is the geodesic from x to y, then the geodesic from x to y is a subset of the union of the geodesic from x to z union the geodesic from y to z. So what that means is that if I have a triangle, 3 points x, y, and z, then the triangle with those vertices is in fact a tripod. The geodesic from x to y is contained in the union of the geodesic from x to z and the geodesic from z to y. Another way of saying this is that there exists some w, some center w in x omega, such that, and here's that center here in this picture, such that the distance from x to y is the distance from x to w plus the distance from w to y. The distance from y to z is the distance from y to w plus the distance from w to z. And the distance from x to z is the distance from x to w plus the distance from x to z. So one way of defining a real tree is to say that this is a metric space in which all the triangles are tripods. Another way to define a metric, a real tree, is that another way to define a real tree is that equivalently the distance, sorry, if gamma and gamma prime are two paths in x omega, and if they don't self-intersect, if they're injective, and if gamma of 0 is equal to, and if they both start at the same point and they both end at the same point, then in fact they're just two parameterizations of the same path. Then in fact the image of gamma is equal to the image of gamma prime. So that means that there's only, given any 2 points x and y in the space, there's only one path from x to y. If I have any other path from x to y, it has to contain that original path. At worst, if I wanted a different path from x to y, I could, like a tree, I could have some branching and some backtracking, but it has to contain that original path from x to y. So in fact, this metric space, this asymptotic cone, is a real tree. In fact, you can say that x omega is a universal real tree, in the sense that if I have any other real tree where the degree of each vertex is at most the cardinality of the real numbers, then it's actually a subtree, a subspace of x omega. So that's one way to actually prove that this doesn't depend on the original degree of the tree, on the original, whether the original tree was degree 3 or degree 4 or degree 5 or anything like that, because no matter what degree you get, you're going to get a universal real tree in this sense. And if I have two universal real trees like this, then they're actually isometric to one another. Is this okay so far? Okay. So one more example. So the reason that I wanted to give these two definitions of real tree is because this definition is very close to something we've seen before. Remember last time I talked about delta hyperbolicity. A space is delta hyperbolic if triangles in that space are thin. If a space is delta hyperbolic if triangles in that space are thin. If whenever I have three vertices x, y, and z, and I draw a triangle with vertices x, y, and z, then the edge from x to y is contained in the delta neighborhood of the edge from y to z, union the delta neighborhood of the edge from x to z. And so this condition of being a real tree is very close to that condition. The difference between this condition and that condition is that this is really zero hyperbolicity. This is saying not just that the edge from x to y is in the delta neighborhood of the edge from x to z and y to z, it's actually contained in the edge from x to z and the edge from y to z. And so, in fact, if x is delta hyperbolic, then the asymptotic cone of x is a real tree. And the reason, and the way we can prove this is that if x is delta hyperbolic, then it doesn't have an exact. Then triangles don't have an exact center like we had over there, but triangles have an approximate center. I can take some point in the geodesic from x to y, that's delta away from the geodesic from x to z, and delta away from the geodesic from y to z, and then this is a delta center. The triangle xyz has an approximate center, has a delta center w, such that the distance from x to y is at least the distance from x to w plus the distance from y to w plus minus 2 delta. Likewise, the distance from y to z is at least the distance from x to w, from y to w plus the distance from z to w minus 2 delta. Likewise, the distance from x to z is at least dxw plus dzw minus 2 delta. And when we take the asymptotic cone, So if xi, yi, zi are in the asymptotic cone, then there's a sequence wi of delta centers of the corresponding triangles. And this sequence wi of delta centers converges to a zero center, converges to an actual center. Then, because what happens, we take this inequality and we take the ultralimit of distance from x sub I to y sub I over I. This is going to be less than or greater than or equal to the distance from x sub I to w sub I over I plus the distance between y sub I and w sub I over I minus the limit of 2 delta over I. This is 0. And so that means that the distance between x sub I and yi is greater than or equal to the distance from xi to wi plus the distance from yi to wi plus 0. And by the triangle inequality, this inequality is in fact an equality. And so this, for the limit of the delta centers of the triangles, is in fact a zero center of this triangle in the asymptotic cone. And so that means that every triangle in the asymptotic cone has a zero center, has a center. So every triangle in the asymptotic cone is a tripod. And so that means that x omega is a real tree. And so the asymptotic cone of any delta hyperbolic space is a real tree. And most of the time, unless your original space is unless your original space is a particularly simple delta hyperbolic space, most of the time this is going to be the same as for as the 3 regular tree. This is going to be the most of the time. This asymptotic cone is going to be a universal real tree. Okay. Are there any questions? Okay, so next time what we will do, we'll talk about how to use this. We'll talk about how to use this to say things about the Dane function, how this is related to the Dane function, and yeah, I think we'll also start talking about Carnot geometry and nilpotent groups and asymptotic cones of nilpotent groups.